Okay, here we're in chapter 3 on determining change. This is derivatives. And section 3.4 is on rates of change of composite functions. So sometimes functions can be given in composite form instead of being presented as two separate functions or three separate functions, and that can be combined through composition. So we're going to be already composed and we're going to have to decompose them basically. And so when a function is presented in composite form, what we need to do is we need to identify both the inside and the outside function. So that's going to be key. We have to determine what's inside and what's outside. And then we're going to use the chain rule for derivatives, and that way we can find a rate of change formula for the composite function. Okay, so before, they might give us an s of t, and that equals something, and then t of x, and that equals something, and then we wanted to find overall the s of t of x. And then we also would find the s prime of the t of the x. Okay, so that was kind of the order we've been doing it. Now we're going to be given this one. We have to break it into these two, and then we're still going to find that. Okay. So if the function is already expressed as a result of a function composition, that is, if it is a combination of an inside function and an outside function that we can actually identify like up here, then its slope formula, the derivative, can be found by taking the derivative of the outside function with the inside function copied, and then the derivative of the inside function, and then multiply those two. Okay, and so let's see what it looks like in our normal way we look at our definition. So if a function f with input x can be expressed as a composition of f as a function of t and t as a function of x. That is, f of x equals f of t of x. So kind of like, what we did here, s of t of x, except we used s instead of f. Then its derivative is f prime of x equals f prime of t of x times t prime of x. Okay, so we're plugging in t of x back into the derivative of the f, and that way we have everything in terms of x. We'll have x here and x here, because when you take that derivative of the f of t, that originally is just going to be in terms of t, and so then you have to plug in t of x into that t, and that way it'll all come out in terms of x. So for example, if we have the function f of x is equal to 7 plus 5 ln of 4x squared plus 3, what is that? Well, if we look at that, we have a long function, but we have something on inside. So the key thing is to look for things in parentheses and stuff like that. And that's usually going to be your inside function. And then everything on the outside of that is going to be your outside function. So, and it says it's going to be the composition of f of t of x. Okay, so f of t is going to be our outside function. So that's going to be the long thing. So that's going to be 7 plus 5 ln. And because we're saying it's of t, we have t. Now we said this was the inside function, which is the t of x. So t of x is just equal to 4x squared plus 3. Okay. Now what we're going to do is we need to kind of basically compute those derivatives. So, if we do that, f prime of t is equal to 5 over t, and t prime of x is equal to 8x, because if we bring our 2 down, then it's 8x. And when you have the derivative of ln of t, that's just 1 over that t. So that's going to be our two derivatives. And so when we plug that in, this is what it looks like. We have 5 over t times 8x. So we're just taking that times that. But we have to plug in that t of here, so that t of x back into here. So we have to plug in this back in place of that. And so when we do that, that goes down there, and we have 5 over 4x squared plus 3 times 8x. Now this is a simple one. We could take 5 times 8 and get 40 times x and get 40x over the 4x squared plus 3. And that's a little bit simpler form, and we didn't have to do too much work. Now if you had one where you have a lot of, maybe at a use substitution, we have three things in here, then you don't really have to simplify it down to the most simple form. We can leave it as our original part, and we're done there. Okay, so that's how we're going to look at these composed functions, and we have to decompose them into the two pieces, and then after that take derivatives of those two pieces and then substitute everything back in until we get back to where we started. All right, so some ideas on how to look at composite models. So these three models incorporate function composition. So if we have an exponential and it's in a form f of x equals ae to the bx, well, we can consider that bx part is going to be our inner or inside function, and a e to the x, or t in this case, we're going to look at it as, is going to be the outside function. So we're going to call f of t is equal a e to the t, and then t of x is equal to b of x, bx. Okay. Now, if we have a sine function, it might look in the form something like a sine bx plus c plus d. That's the full thing. And we might not have a d, or we might not have an a. But if we have a sine of something, that something is going to be our inside function. And so if we're plugging everything in and calling it t of x, that's going to be our t of x. And then everything else left over is going to be f of t. So if f of t equals a sine t plus d. So that's what that is. And then again, once you do this, then you'll take the derivatives of f and the derivatives of t, and that should be a lot easier to actually take those derivatives and actually simplify. Now, our logistic model, it's the one that when we do things, it's the more complex one, because, this here piece is, you have to do a u substitution and do some other stuff and things. And so it's going to be considered the composition of three functions. So we have a c over what we're going to call a s, and that can be written as c s inverse. So that we could have taken that up, and that's all to the -1, basically. Or if we already change it to s, then it's to the -1. Then our s of t is just that whole denominator. But we've already taken out this part here, which is the t, and that's a minus bx. Okay, so we're kind of taking things and piecing them out as we go, so it's a lot simpler. And so we've got c s inverse 1 plus a e to the t and negative bx in this case. Okay. Now, logistic models in a chain rule, basically, what we're going to have to do is we're going to have to use the chain rule more than once when we do the derivative. And that's when we do the u substitution, or in this case, they did the t and s substitution. So it all depends on how you want to look at it, but we're going to do an extra substitution. So we'll have three things to multiply. All right, let's look at another example. So multiple applications of the chain rule. So it can be applied multiple times for functions, and it doesn't always have to be that logistic function. We can actually simplify other functions and do it that way too. So we can look at this, and we have some f of x is equal to 5 plus 6e to the 2x, all that raised to the third power. So what we can say is that, well, something to the third power, we can replace everything in here with a variable. So they said, well, let's replace it with f of g and call it g to the third. So we're replacing all of that with g. Now, what's going to happen is, if that's g, well, wouldn't it be nice to get rid of that e to the 2x and say, well, that is now going to be another letter, and we'll call it h this time. And so we'll say 5 plus 6e to the h, because we can take a derivative of e to the h very easily. And then we say, okay, well, since that's replaced with h, then we have h of x is equal to just 2x. Okay, and we can go backwards substitute, because this is going to be f of g of h of x. And so we're going to plug that into here, and then we'll have 5 plus 6e to the 2x. And we're going to plug that into here, and we're back at this point here. Okay. And so what we're going to do then is we're just going to take the derivative of each of these pieces and multiply it all together to get our final overall f prime of x derivative, okay? All right, so when we do that, that's going to be 3g squared. So that's what we have here. This is going to be 6eh, because eh doesn't change, so that's 6eh. This is a 1, so that's just going to become 2. And so now that's what it looks like. But we want it in terms of x, so we have to get rid of the g and the h. Well, g, we said, was 5 plus 6e to the h. Well, that means we're back to having an h in here, but that's okay. We'll plug it in and say, okay, that's that. 5 plus 6e to the h, and it's squared, and it's still times 3. And now we have h in two places, and we're just going to replace that with the 2x. And so we plug in 2x there. And at that point, if this was much more complex, I would say we're done. But because we can take 2 times 6 times 3 and get 36, and then that's times e to the 2x, and that's times 5 plus 6e to the 2x squared, we can write the final simplified form pretty easily. So on this one, I would say, going down to this step would be okay. And so that's going to be our final form of f prime of x. Okay. Or sometimes we would write df dx as well. So kind of depends on how we want to write it, because then, to get from here to here, what we would be doing is we're going to be df dg times dg dh times dh dx. And that's what we'd have to do to get that. And that's f prime of g, so that's f prime of g. Then g prime of h, that's g prime of h. And that's h prime of x, and that's h prime of x. And so this is one representation, this is the other. Now this one doesn't show that when we take that times that, that cancels, that times that, that cancels, and we get df dx, which is what we want here. But if we know how it all works, we know that that's the same thing. So however you want to represent it, that should work as well. All right, so let's stop there and then we'll start some exercises.